Thank you.
Thank you, Sergei. Actually, in actinide dioxide, I will present you the results of a series of experimental studies that we have performed over now almost 40 years, not continuously, but every 5-10 years we do an experiment where we have a new idea on a system that is apparently very simple, but that turned to be pretty intricate with some properties that required investigation via several techniques to address different aspects of the properties. Now we think that we understand pretty well the ground state of these systems, also the dynamics, but still there are some aspects, especially above the phase transition, that are still puzzling. Anyway, here I will describe you the ground state of uranium dioxide and neptunium dioxide. The plutonium dioxide is less interesting because it's a non-magnetic system with a singlet ground state. I will show you the results that we obtained studying the lattice dynamics and dynamics of the magnetically ordered system with a series of inelastic neutron scattering and inelastic X-ray scattering, including polarization analysis, spherical polarization, time of flight, and several techniques. What is emerging from this analysis is that the key ingredients to understand the physics of these systems is the two-ion quadrupolar interaction, mediated both by the quadrupolar component of the superexchange interaction and by magnetovibrational coupling. The studies at the end put in evidence the existence of a dispersive quadrupolar wave that in a way is similar to so-called orbitons in d-electron systems. And the presence of a number of avoided crossing situations where these excitations are vibrational, spin wave, quadrupolar wave are mixed. So, if you want, entangled in the sense. The systems were first studied during the Manhattan Project. In the 40s, between 42 and 45, Randall and Zachariasen had already determined the crystallographic structures of this compound, which is just the fluorite. You have the actinide forming a face-centered cubic lattice, and the oxygen, an internal cube. So 8 atoms of oxygen forming a simple cube with an internal lattice. The studies, the data were then disclosed at the end of the war in the 50s. Immediately there were studies on the properties at low temperature, and in 52 and in 53, essentially by heat capacity measurements and magnetization measurements, phase transition was discovered both in UO2 and NPO2. UO2 has a first-order phase transition. Notice that here the scale is interrupted and goes from, say, 10 to 300. There is a very huge spike in the heat capacity. First-order phase transition, you see an anomaly in the magnetic susceptibility, and this was interpreted as the occurrence of an antiferromagnetic order. Similar observations were obtained in neptunium dioxide. The transition temperature is a little lower, 25 Kelvin compared to 31 in UO2, but the transition is second order in this case. The behavior of the magnetic susceptibility is very similar, And then it was assumed that also NPO2 was a magnetically ordered system with an antiferromagnetic order. Actually, this was not the case. From 53 to about 2010, a number of neutron diffraction studies, both on powder and on single crystals, and the Mossbauer spectroscopy experiment using neptunium-237, which is a active Mossbauer ions, failed to detect any magnetic dipole moment on the neptunium site. The upper limit set by the experimental sensitivity was of about 10 millibohr magneton. But on the other hand, the muon spin relaxation experiment showed a oscillation in the signal, in the forward-backward asymmetry signal, indicating that a magnetic field was present at the site where the muon were implanted. At that time reversal symmetry was broken. So neptunium dioxide was the first example of what was called hidden order in a system showing a similar puzzle later on, uranium, ruthenium-2, silicon-2. Well, the magnetic structure of UO2 was the existence of antiferromagnetic order in uranium dioxide was demonstrated by neutron diffraction already in the 1957 by these two guys, Henshaw and Brockhaus, in Chalk River in Canada. 10 years later, Willis and Taylor and Fraser et al. Repeated the experiments and proposed a collinear single K structure. But in 1976, another neutron diffraction experiment, this time on single crystal, performed by Faber and Jerry Lander at Argonne, discovered two things that have not been observed before. One was an internal distortion of the oxygen cube, whereas the lattice of the uranium remained face-centered cubic. And then they observed that the structure was not conform to the expectation for a single K. They proposed a non-collinear 2K structures with the moments in the AB plane. This was also wrong. The correct structure was suggested in 1986, and this time the solution was correct. The structure is a type I triple K transverse magnetic structure with a propagation vector 001. The magnitude of the order and moment is 1.74 Bohr magneton is another fact that is difficult to explain. But anyway, so what it means, a triple K structure, it means that on a given site, one of the four sites of the simple cubic cell with the four atoms in the basis that describes the ordered state, well, on each site, the magnetic moment can be represented as the sum of three Fourier components. The sum is made over the elements of the star of the propagation vector, so 1, 0, 0, 0, 1, 0, 0, 0, 1. The structure is transverse in the sense meaning that, for instance, the Fourier component associated with 1, 0, 0 is along 0, 1, 0 and a cyclic permutation. You can have also another alternative, another domain where if the magnetic the Fourier component associated to this vector is not along y, but is along 0, 0, 1 and cyclic permutation. So these two structures, these two domains, have a diffraction pattern which is identical. And it's also identical to the structure pattern provided by a single K structure of a double K structure. So that's why it was not possible before to determine what is the real structure. Actually, this proposal by Paul Burlet in 1986 was also not completely convincing, because what they did was to apply an external magnetic field that, in the case of a single case structure, would have oriented the domain, so magnetic moment along x, y, and z, and then would have altered the relative intensities of some peak in the diffraction pattern. They observed no variation, so it was a zero observation experiment, and then the possibilities were two. Either the structure was a triple K, where the magnetic field has no effect on the diffraction pattern, or the magnetic field was not strong enough to reorient the system. Anyway, in 2007 we performed inelastic neutron scattering experiments using a spherical neutron polarization analysis, which is a technique that allows you to determine the amplitude of the magnetic fluctuations along different directions. This anisotropy in the magnetic fluctuations is a signature of the triple K structure, even in the absence of any external constraint. And so, okay, we confirm that this is what happens in this system. Well, the lattice dynamics of U2 was also investigated by inelastic neutron scattering in the early days. You have 3 atoms in the unit cell, so the uranium, the 2 oxygen, then you have 9 phonon branches. These were measured by Dolling, Cowley and Wood, and by Cowley and Dolling between 65 and 68 at Brookhaven, using the triple axis spectrometer that Brockhaus had invented a few years ago, and that gained him the Nobel Prize in physics. So the phonons were studied, and everything seems okay, very nice. This line are just a rigid ion model. More recently, measurements of the phonons were performed by Bill Byers and collaborators in Oak Ridge, and extended at very high temperature with the aim of studying the phonon lifetime in connection with the thermal conductivity of this material. But back to 68, Cowley and Dolling measured also the excitations in the ordered state. They were interested in observing the spin wave dispersion in this system. Well, experimentally, what is the difference? If you want to observe a magnetic excitation, you have to measure at small momentum transfer. So the Q, the difference between incident and scattering wave vector of the neutrons, must be small, because otherwise the intensity is killed by the square of the magnetic form factors that goes quickly to 0 as Q increases. On the other hand, if you want to measure phonons, you want to measure at high Q transfer, because the intensity is proportional, as a first approximation, to the square of the momentum transfer. Then these experiments were done at low temperature, below in the ordered phase, a small value of Q, and they were sensitive to magnetic excitations without polarization analysis. So there were very surprising results. First, a gap here that was correctly interpreted immediately as an anti-crossing due between this transverse acoustic phonon, the dashed line is what was measured in the paramagnetic phase, and the acoustic spin wave branch, which should be the red line. So an anti-crossing due to magnetoelastic interactions. But there was an aspect of this experimental data that required many decades to be understood. You see, as I will show later, what do you expect even in presence of anisotropic dipolar magnetic interactions are just 2 branches. And the optical spin wave branch should have the same energy at the zone center and at the zone boundary, and at the zone center should be degenerate with the acoustic spin wave. Instead, the experimental data showed here, so 3 branches, this one, and this one. So strong intensities at the gamma point with a gap of about 2 milli-electron-volt. Many attempts were done theoretically to try to reproduce this spectrum, but there was no way out. In neptunium dioxide, similar studies were not performed, essentially because the chemists failed to grow big single crystals of these materials. UO2 is easy to have a single crystal of large size, but with NPO2, it seems impossible. Until now, nobody obtained big crystals. Actually, this is a photo of the crystal where we did most of our experiments. It's a nice single crystal of uranium dioxide. The mass is about 100 grams. This guy here, this is the largest sample of neptunium dioxide which is available. The mass is about 1 milligram, far too small to perform inelastic neutron scattering. You can do elastic diffraction. We did polarized neutron diffraction studies and crystallographic studies and measurements of diffuse scattering, but still, even for diffraction, is very demanding, also because neptunium has a strong absorption cross-section with a resonance at about 270 milli-electron-volt that produce even at the milli-electron-volt range a very strong absorption. Anyway, the dynamics, the lattice dynamics in NPO2 was studied more recently using inelastic X-ray scattering at the SRF. Here, with this technique, you can afford measurements on sample with very small size. On UO2, we use the sample of 10 micron size. So for this machine, our NPO2 crystal was huge. How it was, you see the machine is very long. This is a picture just of the secondary spectrometer, this part here. So you have to perform the measurements using incident photons with very high energy, about 19 kilo electron volt, to have penetration, enough penetration in the sample. And in our case, to be away from absorption edges, the L2 and L3 absorption edges in particular. So very high incident energy. And you want to observe the dispersion of excitations with milli-electron volt energy size. So you need a resolution of about 10 to minus 8. This is achieved by a first pre-monochromator that also remove all the heat coming of the big intensities, sophisticated collimation systems, and using a monochromator in backscattering, so close to 180 degrees to reduce the geometrical contribution to the resolution. The bandwidth is of the order of 10 to minus 8, and then you have a secondary spectrometer, which is very similar to the geometry of a triple axis neutron spectrometer. How is done the scattering? You keep the analyzer inside the thermostat at constant temperature. This is the bank containing the analyzer, so the sample is here. And you do the scan, the energy scan, by heating the monochromator. Then you have a lattice expansion. The lattice spacing, for instance, increases with increasing temperature, and then you change the energy of the reflected photons. Well, in this way, we were able to measure the dispersion curves, the phonon dispersion curves. Here they are compared with the computational results obtained by Peter Openier and Pablo Maldonado using a GGA plus U framework for the electronic structure and the quasi-harmonic approximation. They also calculated the line width of the phonons, which are represented here by these dashed bands. What is interesting for the following is the observation of a sharp peak in the phonon density of state as a function of energy here at about 54 milli-electron volt. Here the green curve are the phonon density of states of uranium dioxide and the black of neptunium dioxide. So this peak is important for understanding the ground state of neptunium dioxide, as I will show later. Actually, another key ingredient is the crystal field potential. In the 60s, there were calculations that were suggesting a very strong crystal field with excitations extending at about 600 milli-electron volt, and then producing a substantial J mixing in this material. We made some attempts of measuring this excitation at ILL in Grenoble, where there is a neutron reactor as a neutron source, using a hot spectrometer called IN1. And we failed because to measure magnetic excitations at high energy transfer, you need to satisfy two criteria: high energy transfer, but small momentum transfer, because otherwise you will kill the intensity via the square of the magnetic form factor. Well, this can be done only by using high incident energy neutrons of the order of 2 electron volt. And nuclear reactors, even with a hot source, are not the best machine because the spectrum, the incident spectrum at this energy is quite poor. So we failed in observing any signal of crystal field in UO2 at the ILL, but in 1986, ICES, a spallation neutron source, started to be commissioned at near Harwell in the Oxfordshire. There, we made the first experiments on a machine that was called the HET, a chopper spectrometer, that had the good characteristics for this kind of experiments. And indeed, we observed the presence of two magnetic excitations, and we were able to demonstrate that there were no other magnetic excitations up to about 800 electron volts. So this was interpreted with a crystal field potential leading to a gamma-5 ground state, a gamma-3 triplet at about 155 milli-electron volt, and then a gamma-4 triplet and a gamma-1 singlet. The spin-orbit coupling in this system is 223 milli-electron volt. This was determined first from optical spectroscopy, and more recently we performed non-resonant inelastic X-ray scattering on the O edges, so 5D, 5F transitions on single crystals, and studying the directional dependence of these systems, you can fix, you can determine the parameters, and you can verify that this value is okay. So gamma-5 triplet ground state. This means that you have 8 degrees of freedom in the ground state. So you have 3 dipole, 2 electric quadrupoles of gamma-3 symmetry, and 3 electric quadrupoles of gamma-5 symmetries. Neptunium dioxide. Neptunium dioxide has 3 electrons in the 5F shell, so the ground state is tenfold degenerate, and in cubic symmetry, it must be split into 2 quartet and 1 doublet. Now, the transition amplitude between the quartet and the doublet in neutron scattering is essentially 0. It's very small and very difficult to observe. Then we were expecting only one peak, gamma-4 transition, because the gamma-4, gamma-2 has no intensity. And instead, with the same geometry of the experiments done for uranium dioxide, we observed 2 magnetic peaks centered at about 54 milli-electron volts. So what was the origin of these things? On the other hand, If you go below the phase transition, this was in the paramagnetic phase. If you go in the ordered state, for instance 5 Kelvin, these are results obtained by a triple axis neutron spectrometer using a polarization analysis. And the red point are in the spin flip intensity in the spin flip channel, so the neutron spin change flip during the scattering. The open points are non-spin flip intensity. And here you observe vibrational intensity, and here you observe just a magnetic signal. So there is clearly a splitting of the ground state, which is not just a splitting into two doublets, because otherwise we would observe only one peak. So this is a signature that something is happening, reducing the symmetry at the phase transition. But it's not magnetic order, despite 5F3, this is a Kramer's ion. And then a non-magnetic singlet is something that you do not expect. Anyway, remain to explain these things. Well, the reason why there is a double peak is because of the presence of a narrow peak in the phonon density of states. This peak is due to optical gamma-5 phonons, which are triply degenerate. They have the same symmetry of the gamma-8 quartet. And then they can mix, forming a crystal field phonon-bound state. The states are split, but if you calculate the matrix elements in the dipole approximation for neutrons, you will see that only transition from the ground state to the band edge of this object have intensity different from 0. Then what you expect in an experiment is to observe transition from here to here and from here to here. And this is what we observe. If you want to detect the bare crystal field, you should go to high temperature, because then the electron-phonon coupling becomes weaker, and this formation of the crystal field phonon-bound state should disappear. With neutrons, this is not feasible, because if you increase the temperature, you increase also the background due to the diffuse scattering. But you can detect this bare excitation using Raman scattering. For an FCC lattice, Raman scattering, you would expect only two peaks here, one which is the gamma prime 2,5 phonon, and this shoulder here, which is the longitudinal optical phonon at the gamma point. But the line here at 350 Kelvin is asymmetric, and this line shape can be fitted by the sum of three lines. If you do these measurements at several temperatures, you will observe that at high temperature, for instance around 800 Kelvin, the line becomes symmetric, and actually the intensity of this feature goes down with temperature. Then it's an electronic excitation. If it were vibrational in origin, it would increase with temperature. Okay, this is at 54 millielectron volt, and we attribute this to the gamma-8 bare crystal field transition. So gamma-8 ground state means that you can now have magnetic degrees of freedom up to rank 7. You have magnetic dipole, octupole, triaconta dipole, rank 7, in addition to electric quadrupoles and electric hexadecapoles. Okay, what happens to all these degrees of freedoms? We knew that in uranium dioxide, the magnetic dipoles order, and we knew the structure, triple K transverse antiferromagnetic. To detect the order of electric quadrupoles is more tricky, because quadrupoles do not couple with neutrons. So you cannot observe quadrupole ordering directly with neutron scattering. You can have an indirect indication only if you observe a distortion of the lattice. Instead, you can observe these excitations using resonant X-ray scattering or resonant X-ray diffraction. So what you do is you tune the energy of the incident photon to an absorption edge, for instance, the M4 or M5 edges of uranium or neptunium. So transitions where you excite an electron sitting in the spin orbit split 3D state to an empty 5F state. Then, when the electron fill the core hole, you will have an emission of a photon with the same energy of the incident photon. If you have a coherence, you will observe diffraction associated with this resonant two-phonon process. Well, the presence of the resonance introduces in the susceptibility terms that are anisotropic. In the scattering amplitude, you will have the sum essentially of two terms, a dipole and a quadrupole term in the transition. It comes just by the expansion of the vector potential, and you keep the first two terms. One gives rise to dipole excitations, the other to quadrupoles. In the amplitude, then in the intensity, you have dipole-dipole, dipole-quadrupole, and quadrupole-quadrupole terms. These excitations are coupled to order parameter of different rank. Here, charge, magnetic dipole and electric quadrupole. Here, in addition, magnetic octupole. And here, in addition, also electric hexadecapole. How can you disentangle all these contributions? Well, this you can do because, first, they occur at different energies. Dipole-dipole will be at the white line of the absorption edge. The others will appear in the pre-edge. Then, by tuning the energy, you can optimize the intensity coming from the different things. Then, in addition, the polarization dependence of this scattering is different. I mean that the intensity changes in a different way when you change the direction of the linearly polarized photon and analyze the polarization of the linearly polarized diffracted photons. Then you can do polarization analysis of incident and scattering beam and also have a way to distinguish what happens. A third quantity that changes in a different way and is related to the motif of the order is the modulation of the intensity in a given Bragg peak when you rotate the sample. When you rotate the sample about the scattering vector. So you have the scattering vector like this, incident and diffracted, and you rotate the sample around this direction. If you have a charge order, the intensity is flat. If you have a magnetic or quadrupole order of different orders, you will observe oscillation. For instance, these are the oscillation observed in the intensity of the 112 Bragg peak, which is forbidden in the paramagnetic phase of U2, which is an FCC. For incident photons with polarization, sigma is for senkrecht, so perpendicular to the diffraction plane, and diffracted photons also with polarization perpendicular to the diffraction plane. And this angle here is this azimuthal angle, rotation about the scattering vector. Well, the solid line here corresponds to ordering of gamma 5 electric quadrupoles in that on each of the 4 sides of the simple cubic ordered uranium lattice have the linear combination here, plus, 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 minus, plus, minus, and so on. So this combination corresponds to a triple K transverse orders of electric quadrupoles as depicted here. The different colors are for the different 4 sides. So we have magnetic order associated with electric quadrupole order as a secondary order parameter. If you study the temperature dependence of the order parameter, you will see a first order transition for the magnetic order, and something going like this for the quadrupole. It's also clear why, in this situation, there is an internal distortion of the oxygen cube. Look at this picture. Imagine this is from above, from the 001, and these lines are the body diagonal of the cube. The green candies represents the aspherical electron distribution around the uranium atoms in the order. So it's clear that the negative oxygens, these two, for instance, A and C, will be pushed toward the center from the excess of charges here, whereas B and D will be pushed away from the center. And then you will expect a triple K distortion of the oxygen cube. The amplitude is small, 0.08 angstrom of displacement, but can be clearly seen in charge X-ray diffraction or neutron diffraction. Well, neptunium dioxide. As I told you, it was a mystery why there is this phase transition with very large change in the entropy, clear signature in susceptibility, but nothing to observe in diffraction and so on. Similar experiment with resonant X-ray scattering. Here, the sigma-sigma channel in blue and the sigma pi channel in yellow, I don't know, at the 003 forbidden position in the FCC lattice. In this case, the results can be modeled assuming zero magnetic dipole moment, but an order of the electric quadrupole of gamma phi symmetry, an order which is similar to the UO2, but in this case is longitudinal. So it means that the Fourier component associated to 100 is along 100, the one associated to 010 is along 010, etc. So here you see the charge distribution is such that do not perturb the position of the oxygen atoms that remained in the special position 141114, although this point group is reduced. So no crystal field, the point symmetry is reduced. However, muon spectroscopy shows oscillations in the asymmetry intensity signal, indicating the presence of a magnetic field. In addition, if the quadrupole order were the primary order parameter, then the gamma 8 would be split into two doublets, and we would observe only one peak. Instead, we observe a more complicated system. This is because the primary order parameter are the magnetic multiple of rank 5, the Triaconta dipole, and these are the reproduction of the spectra. So the first peak corresponded to an excitation where the quadrupole is tilted and the Triaconta dipole is quenched, and this one corresponded to an excitation where the Triaconta dipole is reversed and the quadrupolar system is unaffected. Okay, well, dynamics, collective excitations. The main ingredients are crystal field, magnetoelastic coupling with oxygen displacement, superexchange. Crystal field determines the ground state, the unquenched multiples, and their polarizability. On the other hand, magnetoelastic coupling provides two ions multipolar interaction, coupling electric multiples. Superexchange provides instead two ions dipolar and multipolar coupling between magnetic multiples and electric multiples. So if in the order phase the degeneracy of the ground state is removed, we have a gamma 5 states, it's a triplet. We can model with a pseudo spin equal 1 with components -1, -1, 0, and 1. There is only one dipolar single ion excitation possible involving Jx and Jy. So all the other 6 degrees of freedom would be frozen if we consider only dipolar single ion excitations. If you have only one excitation, you have 4 sublattice, then you expect 4 excitation branches. along the 001 direction, two degeneracy spin acoustic branches and two degeneracy spin optic branches, with what I said, the same energy here, and this degenerate. But the experiments are more complicated. So these are the dispersion of the magnetic modes. Here, green means high intensity, and so small, low intensity, and brown, high intensity, so qualitatively. But it's much more complicated, and there is this branch. Of course, we are forgetting an important ingredient. There are also quadrupolar transitions that are coupling, operators that are coupling these two levels. So we have a quadrupolar contribution in the -1 to 0 transition, and a purely quadrupolar transitions coupling -1 to 1, qxy and x squared minus y squared. So now we have to consider two single ion transition with 4 sites, so we have 8 excitation branches. And of the 8 degrees of freedoms, only 2 are frozen, Jz and Z squared. Here, the quantization axis on each of the 4 sites is along the local one of the 111 directions. Okay, so if you want to study the couple dynamics of the systems, it's nothing special. It's only technically complicated because you have 60 dynamical variables to take into consideration simultaneously. We have 12 dipoles, 3 for each of the 4 sublattice. So you have 12 quadruples, and you have 36 atomic displacements. So the Hamiltonian must contain a spin-spin and a quadrupolar super exchange interaction, then the phonon, the bare phonons, and the quadruple phonon magnetoelastic coupling. The simplest possible model, because you don't want to have too many parameters, must include 2 parameters for the dipole-dipole super exchange in order to allow for an anisotropy, 2 other parameters for the quadrupolar super exchange, and no parameters for phonons if you have the experimental data and you fit this with the rigid ion model. And then you need 2 parameters to describe the magnetoelastic coupling, because you can keep only 2 normal modes of the cubic oxygen cage, the 2 that have gamma 5 symmetry as the quadrupole that you are considering. Well, a aspect that must not be forgotten is that you need a frequency-dependent, so a retarded effective potential describing the phonon-mediated quadrupole coupling. This is simple to understand. Quadrupoles are anisotropic charge. If I change the orientation of this charge, this will perturb the position of the oxygen. So this corresponds to a superposition of lattice phonons. These phonons will propagate, will distort the oxygen cage around the neighboring uranium site, and this distortion of the oxygen will upset the orientation of the electric quadrupole. So you have a quadrupole coupling mediated by phonons, but this is retarded. Another thing that is easy to understand is that you have to expect a mixing between quadrupole and spin wave branches. Suppose, for instance, that in site 1, you have fluctuations of these 2 quadrupoles that couple -1 to +1. Then at site 2, you will, the ion will feel a time-dependent quadrupolar field that can induce off-resonant oscillations of these 2 quadrupoles. But these 2 quadrupoles are locked to Jx and Jy. And then the quadruple excitations oscillation of these 2 objects will induce a spin wave. So the quadrupolar branch here is accompanied by an excitation with magnetic character that will have the same dispersion of the quadrupolar one. And this is why we are able to observe with neutrons excitations corresponding to this branch. Actually, this is the generalized susceptible. So the scattering function calculated the energy as a function of momentum transfer along 0, 0, 1, calculated with random phase approximation and with the model that I described before. And these are the experimental data. You see that we are able to describe all the experimental features. We can observe here the large phonon coupling, but there are also other avoided crossing here. And we can explain why there is intensity here, strong here, and here. It's not just like that. This excitation is just a quadrupolar optical branch. These are wave-like oscillations of the orthorhombic quadrupoles that are associated to a precession of a small spin component which is due to the mixing with the spin wave branch. So let's see some results. Actually, for instance, this anti-crossing here is due to these two quadrupoles that couple phonons to this transition. The transition is at about 7 millielectron volt at C045. But we have others anti-crossing. That's the transverse phonon does like this at room temperature, but here is mixed. We have a splitting, we have another splitting here, and so on. The model also predicts quadrupolar acoustic branches. These are tricky to observe because they are far away from the spin excitation, but you can observe through the mixing with the acoustic phonons. Actually, at the mixed, for instance, spin phonon character means that the wave functions is a superposition of a spin wave component and a vibrational one. And the mixing will be maximum at the avoided, at the crossing position, at the avoided crossing. How we can observe this? For instance, these are inelastic neutron scattering without polarization analysis. We have scanned along these lines. So from 0.8 to 0.2, the crossing will be here at 0.45, 0.5. You see that here we see just the magnetic excitations. Here we start to see the phonons. We are here. Then at the crossing position, you would observe, you would expect only one peak at this energy. And instead, you see that there is a splitting remaining. It's the the avoided crossing and so on. Then they swap the interaction. Here now is now the phonon, and this is the magnetic. If you do a scan like this, here the big Q, the momentum transfer, is moving from 002 towards 000. The quasi-momentum of the phonon is along this direction, so it's parallel to Q. The phonon is transverse. It means that it's oscillating in this direction. So Q dot E is 0. The intensity should be 0 because it's proportional to Q dot E squared. Instead, we see in this scan two big peaks of almost equal intensity. Well, this is because what we are observing is the magnetic component of the mixed mode. Or if you want, the polarization of the phonons at the anti-crossing is changed from linear to circular. What you observe with the inelastic X-ray scattering. So I said that if you want to observe magnetic excitations with neutrons, you have to keep Q as small as possible, and you have to go to low temperature to kill the phonon background, the vibrational background. With X-rays, you do not have these problems because essentially you couple only with a vibrational system. You see only phonons. And actually, you observe easily uranium because we have 92 electrons. The intensity is proportional to Z squared. But you do not expect to observe the electric quadrupoles because these are due to only 2 electrons out of the 92 that are around the uranium atom. So if you observe quadrupolar waves, it's again through the transfer of intensity to mixed mode with phonon characters. So here are, for instance, the same scan as before, propagating along 001. In the ordered phase, here you go, okay, the crossing is about here. And as you see, instead of 1 phonons, we observe 3 excitations. that are colored here with red, blue, and so on. You can follow these points, and these are the excitation, the dispersion of the three features that you observe. The open points are the magnetic intensities measured by neutron scattering. So what you can observe with these two techniques are the magnetic component of the mixed mode with neutrons, the phonon components of the mixed mode with inelastic X-ray scattering. Then you can also measure the phonons with X-rays. And you see in particular that we see no splitting along the 1-1-0 direction. So here is again the results superposed to the magnetic intensity map. You can recognize easily not only the anti-crossing here, but also here. You can observe here peaks that are due to the hybridization with acoustic quadrupolar waves and optical quadrupolar waves. For instance, you can compare the consistency of the results. For instance, look at these peaks. This is the same excitation. So propagation vector 03 along 001 with X-rays and with neutrons. So here, for instance, 03, we see only one peak. This is a phonon. It's this phonon here. That's the dispersion, this transverse acoustic phonon. We see this in the non-spin flip channel with inelastic neutron scattering. In the spin flip channel, the red points, you do not observe because you see only magnetic excitations. Here you see no magnetism, and here you see the magnetism, the excitation here, here, and here. Okay? If you go to Eiger, for instance, 06, here you have 3 peaks in the inelastic X-ray scattering of vibrational origin. This is the non-spin flip channel on the same excitation group with neutrons, non-spin flip channel, then vibration, and you see that you have a big phonon peaks here with 2 wings, and these are due to the anti-crossing with the other transverse acoustic phonons with spin optical and quadrupolar optical branches that split the phonons, and you observe an excitation here and here, and you observe these ears and here. And here in red, in the spin flip channel, the magnetic contribution. Well, this kind of studies give access to more much richer information than just the study of static properties. For instance, this figure shows the Fourier transform along 001 of the static quadrupole coupling arising either from superexchange, are these 2 lines, or from the Jahn-Teller interaction, red and black. Okay? Well, X point is the wave vector for the static order. And you see that the Jahn-Teller quadrupole coupling here is 0. Then the transition is driven by the superexchange quadrupolar interactions. It's an electronic transition that induces the ordering of the quadrupole, the distortion of the lattice. It's not the lattice that distorts because of the coupling with the phonons and induce the transition in the electronic systems. Well, last slide, just to show.
How do you estimate here the Jahn-Teller?
This is from the model for fitting in the random phase approximation, we have the superexchange parameters. These are fixed.
The Jahn-Teller is connected with the G parameter in the model.
With the K parameter in the model. In the superexchange is described as the sum of the dipole and the quadrupole. You have to choose the quadrupole to these 5 parameters that I've shown to reproduce the main experimental observation, transition temperature, order and moment, and the dispersion scape. Then you have the K, and this is just the Fourier transform. Okay. These are just the conclusion that we can observe the mixed character of the excitations, the importance of the orbital degrees of freedoms in systems where these are not quenched, the interplay between spin, orbital, charge degrees of freedoms, the fact that you can observe propagating quadrupolar waves, this is similar to the orbitons problems in the perovskite, if you want. It's also a kind of orbital excitation, but you can describe this in a simple term. And in neptunium dioxide, we have, if you want, an exotic order parameter, but also the demonstration that maybe when you have experimental results that you cannot explain, and you start inventing a sophisticated moment with hypes and so on, and maybe there is a simple explanation that still can be described in terms of well-behaved physics. So, I mean, I could call a phonon a Nambu boson because you have a broken translational symmetry, and then I write a paper instead of the dispersion of the phonons. I say, oh, that's old physics. I talk about an interaction of a Nambu boson with a quadruplon and so on, and it looks something exotic, but it remains the same stuff. Then I guess we should be more careful. Anyway, that's all. Just the collaborators, Giuseppe Moretti, Stefano Carretta, Paolo Santini in Italy. Arno Is, he was at the time at ILL, now he's at ESS. Nicola Magnani was with me first in Parma in Italy, then he followed me in Germany, now he's in Holland. Pablo Maldonado and Peter in Uppsala, Louis-Pierre Regnault, the ELL, and Jerry Lander is everywhere in different installations. So it's a study that started with my thesis in 1980, and we are still doing experiments. Now we are doing RICS in the soft range to observe intermultiplet transitions that are difficult to observe with neutrons, but can easily be observed at the N and O edges, so 4F, 4D, 5F, and 5D, 5F transitions with these techniques. So that's all.
Very impressive.